5.4.1 preview activity. And this is from 2.7. Okay, so the book says, remember how to do the product rule for derivatives? Find the derivatives of each of these products. So g prime of x. Now, if you were in one of my classes before, I like to call this A and B, and then I can do ABBA, the musical group. A prime B plus B prime A. You take the derivative of one times the other, and then the derivative of the other times the one. So we get the derivative of x is 1 times sine x plus the derivative of sine x is cosine x times the a, which is x, and that would be the derivative. If I do this one, h prime of x would be derivative of x is 1 times e to the x plus derivative of e to the x is e to the x times a, which is x. And if I wanted to, I can factor out an e to the x, and I get 1 plus x. But either way is fine. And then p prime. So the derivative of x is 1 times ln x plus the derivative of ln x is 1 over x times the first. And this is 1, so it's just ln x plus 1. This one, the derivative of x squared is 2x times cosine x plus the derivative of cosine x is negative sine x times x squared. I could factor out an x, but it's not going to look a whole lot simpler. I could make this just subtracts instead of plus and negative. But yeah. And then r prime of x. Oh, that was q prime. So r prime of x would be derivative of e to the x, which is e to the x times the second, plus the derivative of the second, which is cosine x times the first. And there's e to the x in both of them, so I could factor that out. Now, you should probably practice doing these without watching me do them, and then see if you get them right. Now, to do the antiderivatives, well, fortunately, they gave us some nice ones to work with, because product rule is not easy to undo necessarily. So the antiderivative of x e to the x plus e to the x, well, that's what we had right here. So the antiderivative would be x e to the x plus c. And this e to the x times sine x plus cosine x quantity, that looks like what we just did in r, so that's the derivative of that. So the antiderivative is e to the x sine x plus c. Okay, what about 2x cosine x plus minus x squared sine x? Well, that looks like what q prime of x was, so the antiderivative must be x squared plus cosine x plus c. And this one is x cosine x plus sine x. That looks like what we did for g, so it must be, the antiderivative must be x sine x plus c. And this last one, 1 plus ln x, looks like this. So the antiderivative must be x ln x, of course, in absolute value when you antiderivative, plus c. However, how would we do it if we hadn't happened to have done ones very much like this? Could we do something like x cosine x? And notice all these produced a plus because they were products. And this one doesn't have a plus. So what can we do? Well, whether you call this AB and the derivative of AB is A prime B plus B prime A, or if you called it fx g, capital G of x, and took the derivative of it and got the derivative of the first, which is small f of x, times the big one, g of x, plus the small g of x, the derivative of g, times the non-derivative of f. That's kind of messy looking. We could have also did it d f of x times g of x dx is f prime of x times g of x plus g prime of x times f of x. Any one of those works, but it's real typical for text to use not A, B, B, A, or F, G, G, A, F, or same here. They like to use U and V. So the derivative of UV dx would be U prime V plus V prime U. And if you took the antiderivative of this side, you just get UV. If you took the antiderivative of this, well, not so obvious, so we're just going to write the antiderivative of U prime V plus the antiderivative of V prime U. Now, in this, we could subtract either one of these from the other side. So I'm going to just write it UV minus, let's say I subtracted this one. Then it would equal the integral of V prime U. Or we could have subtracted this one from both sides, and we would have had UV minus the integral of V prime U equals the integral of U prime V. So it really doesn't matter which way you remember this, other than you know it's going to be the product of U and V, subtract the derivative of one times the other, and then it's going to equal the derivative of the other times the one, derivative of the other times the one. So these two switch roles as far as being the derivative and not the derivative. This was a derivative, not the derivative. Now it's the derivative, not the derivative, in opposite order. So now we're going to use that to do this problem. We're going to use one of these. It really doesn't matter which one you look at. We just got to remember how the pattern works here. So we're going to look at this problem, and we have a choice of either letting U be x and V prime being cosine x dx. Let V prime be this part, and U be this part. Or we could let U be x, cosine x, and V prime be x dx. Now, so we got two ways to start this one. I want to talk about the advantages of each of these. Boy, I hope that wasn't off the screen. So we got the choice of letting it be u being x and then the rest of this being v prime, or letting u be cosine x and the x dx being v prime. So to do this one now, notice that we need to know u and v. So I need to do the antiderivative of this. And if I'm using u and v prime, that's this one, so I'm going to need to know u prime and v. So I need the antiderivative for there, and I need the derivative yeah, I'm using this one. I'm going to call this, and so it's either v prime is this or v prime is the other part. But I'm looking at this one, and I want to go backwards, so now I'm going to need a u, a v, u prime, and v. So if I work with this choice of u and v prime, then u is x, v is the antiderivative of cosine, which is sine. So v would be antiderivative of cosine, which is sine of x. And minus, now the opposite of these two, so I got to do these two, which is the derivative of u is du, and the derivative of x is dx. So I get minus the integral of these two, which is, because I need du, the derivative of u times v, and v is that, so du times sine x sine x dx. Du is dx. So I either got to work with this, or if I switch them, I still need to know uv. So u of v would be the antiderivative of this, which is 1/2 x squared. And the derivative of this, du, would equal the derivative of cosine. It's negative sine x dx. So I'd have uv, which is 1/2 x squared, cosine x, that's the uv, minus the opposites. So I use these two, so now I got to use these two, minus the integral of these two multiplied. So that's 1/2 x squared and a minus, put it out there, sine x dx. So now I have to continue either doing this one or this one. This one looks more complicated than my original one. This one looks simpler than the original one. And that's because I needed to take the derivative of x, which is 1, as opposed to the antiderivative of x, which is 1/2 x squared. So I'm going to continue with this one, x sine x minus the integral of sine is negative cosine x plus c. Minus a minus changes to plus. Now I want to check my answer. Is this really the antiderivative of x cosine x? So I'm going to take the derivative. Okay, I got a product here, so I'm going to take the derivative of x, which is 1 times sine x, plus the derivative of sine x, which is cosine x times the first. Then I got to take the derivative of cosine, which is negative sine x, and the derivative constant, which is 0. These two cancel out, and I actually do get x cosine x. So this must be the antiderivative of that, because I take the derivative of it and I get that. Now, I'm going to show you how I like to set these up using a little bit of a table to help me stay organized. So I'm going to start with a new one here. And notice that, yeah, taking the derivative of the x got simpler. Doing the antiderivative of the x got more complicated. So here, I'm going to make a table, because you noticed I needed to know the antiderivative and the derivative of both u and v. So u and v, the function and the function's derivative. So the t, I'm going to let be u, so that when I find its derivative, I get 1 dt. And therefore, I'm going to let the rest of this be the derivative, because it's got a dt, e to the minus t dt. I'm going to be the derivative of v. So now I'm going to find its antiderivative, which would be e to the negative t, but then if I took the derivative, I'm going to negative, and I don't want a negative, so I have to put a negative on it. All right, if you set this up this way, then the pattern's going to be easy to follow. This is u and v. We always start off by u times v minus, we chose u, we chose u and dv. So we have to do the opposite of those in the integral here. So it's going to be opposite of those, which is negative e to the negative t times 1 dt. So the u, v, is t times negative e to the negative t. So that's negative t e to the negative t minus, and then we have a minus in the integral when we do these two. So that'll change it to plus the integral, the antiderivative of e to the minus t dt, and that we already did once. It's negative e to the negative t. So we get, finally, negative t e to the negative t from this, plus, and this turns into a negative e to the negative t plus c. So, when we do the antiderivative, we get us plus c. Let's check this. Let's take the derivative of this and make sure it comes out to be t e to the negative t. So we've got two parts here. The derivative of the first is negative 1 times the second, plus the derivative of the second, which is negative e to the negative t. Derivative of e to the t is e to the t times the derivative of the inside, which is negative 1. That's why it's negative. Times the first, plus the derivative of this one, it's negative, or subtract, and then the derivative of that is a negative e to the negative t. So this turns out to be plus e to the t. This is minus e to the t. Those two cancel, and we get minus and minus. That's plus t e to the negative t, which is what we were trying to find the antiderivative of. So this would be the antiderivative of that. Okay, now I want you to notice another thing here. We got three terms from this. There was this, which when we took the derivative, we got two terms, and then we got this integral, which is a third term, and that third term canceled one of these two. When we took the derivative of what we had here, we got the product rule on the first part, and we got the integral of this, created this piece, and that piece canceled one of these two. That's kind of what we're doing when we're doing the product rule. We're creating a new integral that'll cancel one of the two parts of the derivative of uv. That's what's going on. All right, so let's try doing another one. So this time, I'm going to hopefully get you folks used to doing a table, the function and its derivative. I think I want to take the derivative of the 4x because that gets simpler. So 4x, its derivative before dx. Which means I'm going to let the rest of this be my v prime dx. So then to do the antiderivative, see, that would have to be negative cosine of 3x. But if I took the derivative of that, I'm going to get times a 3, so I have to divide by a 3. So I'm going to make it 1/3 cosine of 3x. Okay, so here's what I got to start with. So it's always going to be the opposite diagonal in the integral over here. So it's going to be uv, which is the top row. So I'm going to have 4x times negative 1/3 cosine 3x. That's uv minus, since I use these two to create those two, those are the two I'm going to use in the integral. So I got a 4 dx, and I have a negative 1/3 cosine 3x. Got a little scrunched together there. So let's look at this a little more closely. So that's negative 4/3 x cosine 3x minus a minus, so that's plus, the integral, and there's a 4 and a third, and so that 4/3 comes out, the minus cancels the minus, and I'll still have the integral of cosine 3x dx. So I used these two in here, the opposite diagonals, and the top two for the uv. And I think I can integrate cosine of 3x. That's simple enough. If you have trouble with the 3, you can do a separate u, or maybe call it w, equal 3x, and do a substitution and figure this one out. But we're going to get negative 4/3 x cosine 3x plus 4/3, the integral of cosine. See, the derivative of sine is cosine. But then there'd be times that 3 from the chain rule, so we have to do 1/3 plus c. Now let's check ourselves. Let's take the derivative of this and make sure we get 4x sine of 3x. So this is a product. So I'm going to take the derivative of the first, which is negative 4/3 times cosine of 3x, plus the derivative of cosine of 3x is negative sine 3x times 1/3, derivative of the inside, times the first, which is negative 4/3 x, plus 4/3 times 1/3, derivative of sine of 3x is cosine 3x times 3, plus the derivative of the constant is 0. Is that 4x sine of 3x? Sure looks messy. Let's see here. This 3 would cancel the third, so I get 4/3 cosine 3x minus 4/3 cosine. Oh, good. Those cancel, just like on the other ones. And what do we have here? I'm nervous. Oh, I was taking, when I was going to here, I'm taking the derivative of cosine. So I have the derivative of cosine of 3. So that's 3 sine. I've got to multiply by that when I take the derivative. I made a mistake there. So then I've got negative 3 times negative 4/3, which is plus 4. And there's an x. And then there's sine of 3x. And that's what I wanted. Yep, I made a mistake when I did the antiderivative, when I took the derivative of cosine 3x as 3 sine of 3x and minus. Got to be careful of your signs. Okay, couple more. Let's see, we got, set up my table. U, V, F, F prime. Again, we got that variable there, so I'm going to let that be the U. So du, the derivative, that's just going to be 1 dz. And then I got secant squared z dz. So that's going to go here. So the antiderivative of secant squared is tangent. So I took the antiderivative of this and the derivative of this. So this is going to be uv straight across z tangent z. And we set it up doing these two. So now the integral is going to be of those two minus the integral of tangent z times 1 dz. And some of you may not remember what the integral of tangent of z is. So let's remind ourselves. We did that in the substitution section. We said if we have to do the integral of tangent of some variable, dx, I'm going to do dx, we say, okay, let's do tangent is sine x over cosine x. Let u be the cosine x. du would be negative sine x dx. So I divide by the sine, and I get du over negative sine x equals dx, and you divide by negative sine. So this becomes the integral of the antiderivative of sine x, cosine x is u, dx is du over negative sine x. The sine x is canceled, but not the negative. So I got negative integral of 1 over u du, which is negative ln absolute value of u plus c. And u was cosine x, so it's negative ln cosine x plus c. And if you let the negative go up, it becomes ln secant of x plus c. Either one of these works for the derivative of the antiderivative of tangent, and we have to do that. So I'll call it z tangent z And minus, I'll just use the minus one, so the minus will cancel, be plus ln of cosine plus c. Now let's check and make sure that really is the antiderivative of z secant squared z. Take the derivative of this. The derivative of z is 1 times that, plus the derivative of tangent is secant squared z times z. That's what we wanted. So hopefully this tangent will cancel out, plus derivative ln, well, see, that's 1 over what's inside, times the derivative of the inside, which is negative sine x, and the derivative of c is 0. So this is negative sine over cosine, which is negative tangent, cancels the positive tangent, and we get what we wanted. Now, haven't done this one yet in class. I'm going to do this first thing next time, but if you're watching the video, I'll let you see this. Up till now, we've been letting u be the x, and it's nice because the derivative then goes to 1. ln is an exception. We never like to integrate ln, and so if I put ln in here, it becomes messy. So here's one where we're not going to follow the pattern that we've been doing all along. We're going to do the table. We're going to do the same rule, but we got to not use the pattern setting this up. We're not going to let u be the x. We're going to let ln x be the u, and we're going to do x dx down here. The derivative of ln is a lot easier. That's 1 over x dx. The integral of an x is 1/2 x squared. That's what got more complicated way back in my intro that we didn't care for over here. But now it's gonna work out okay. So once again, we do uv straight across. So that's 1/2 x squared ln x. Minus the integral. We use these two off here, so we're going to use the other two. So it'll be 1 over x dx times 1/2 x squared. And this x cancels one of the x's, and the half comes out. So we just have the integral of half of the integral of x, and the integral of x is 1/2 x squared. So we're going to get 1/2 x squared ln x minus the integral minus 1/2 times the integral of, I pulled the half out, integral of x is 1/2 x squared, and plus c. So we get 1/2 x squared ln absolute value of x minus 1/4 x squared plus c. Let's check it by taking the derivative. We want to get x ln x. So the derivative of the first, 1/2 x squared, would be 2 times a half is 1x, times the derivative times the second, ln x, that's what we wanted, minus derivative of ln x is 1 over x times that, which is 1/2 x squared, minus, and we got 1/4 times x squared, which is, why is this minus? It's plus. When we take the derivative, it's this plus. And this one, we take the derivative, it's 2 times the fourth, or 2/4 x to the 1. And the derivative constant is 0. So that's 1/2 x, and this x makes this plus 1/2 x. These two cancel, and I get what I want.